Start recording. Okay, so last time we talked about the solar system, and we talked about everything in the solar system except for the largest and most dominant object in the solar system, which would be the sun. Okay, so remember, we can't, as we look through the solar system, as we look through space, we've concentrated on what is observational, right? Oh, what can we see? And how do we see it? And so the sun, unlike the planets and other objects in the solar system, which can be pretty faint except for the moon, the sun is pretty spectacularly large and bright. In fact, you shouldn't look directly at it. It's too intense and it will burn out your retina. But that being said, the sun is the major player. You may have seen it was tucked in there, but the sun contains about 99% of the mass of the solar system. So if you add up all the mass of all of the planets, all of the meteors, all of the comets and everything, you only get about 1/100th of 1% of the sun's mass. So the sun is the solar system. Now, interestingly, and this is more on a technical note, because all of that mass is located in the sun and everything is much smaller, that actually makes it possible to have stable orbits and predict, navigate satellites throughout the solar system. If the sun if planets were on the scale of the size of the sun, and along with the objects we launch as well, the problem would be unsolvable and everything would be chaotic. But before looking at technical issues, let's go back to observations. So the first thing when we look at the sun is we want to try and see if we can come up with an explanation for why does it shine. All right, so does anyone want to take a crack at it? Why does the sun shine? I feel like Dora the Explorer with the weird paws. um, so anyhow, well, so it heats. So the heat it produces is an effect of it shining, right? It shines and that gives us heat. So that's good. That's a good stab. But when you look at it, you might be inclined to think that it's on fire, right? But fire is, in this day and age, particularly not mysterious. Fire is really just a chemical reaction of combustion. And when something combusts, it expends energy. And we can look at with spectroscopy the makeup of the chemicals in the sun, the molecules, and figure out how much, get an idea of how much chemical potential energy there would be in the sun. And when we do that, that can tell us if the sun is on fire. It looks like it's on fire, but sometimes just because you look like a duck doesn't mean you quack like a duck. So we can look at through spectroscopy, we can see the energy content and look at the potential energies just by sort of ballparking the number of atoms, which is easier to do than you think. In order to do something like that, you just need to know the number per some small unit volume, right? And once you get this number, you figure out what fraction that is the volume of the sun. And then if you figure out the number in that small volume, multiply it by the big volume, you get the number of molecules in the sun. And it's just multiplication, sort of reorganizing the math. Now, reorganizing the math is not trivial. That's hard to do. But and what I mean by that is putting the science into math terms. But it's pretty straightforward. So that's one way of calculating the available fuel of a fire, right? Now, we can also look at the luminosity, just the brightness of the sun. And once we get the distance to the sun, we can figure out how much power is being output by the sun. And so basically, if we know how much fuel, if you think of it like a car, right? So we have two measurements. One is how much fuel the gas tank can hold. So we know how much total fuel we have. And then that's the chemical energy content. That was a poor circling, but I think hold on. I'm going to draw so the chemical energy content, let me get the chemical energy, this is like the gas tank. So that gives you the total energy, right? And the luminosity tells you how much gas you use per year, or gas per second. All right? So if we have a total amount, and then the amount per second, when we divide that, those will be gas and gas, you'll get something in time. And when you convert it to years, you get about 10,000 years. Okay? Now, there's a problem with that. We can date, and we have other processes like radiocarbon dating and rock age that indicate a much older solar system. And in fact, we have very compelling evidence for processes that predate 10,000 years ago. In fact, we can date some human activities to longer than 10,000 years ago. But the sun should only be alive if it's on fire for 10,000 years total. All right, so this number is inconsistent with other data. So all we can conclude is that, and it's wildly inconsistent, right? Several orders of magnitude. So in this sense, we assume we rule out a chemical reaction, right? It's not fire. But now you might ask yourself, you might go, well, Self, what about, we know that that where the sun really comes in handy, or comes and dominates, isn't so much in what it's made of, but how much of it there is, and that the gravity of all that stuff would lead to it contracting gravitationally and then emitting heat and just becoming hotter and hotter the more it contracts. And that's a good thought. But again, we can look at the energy output in gravitational potential energy, right? Again, our top value is like our gas tank, and we're still seeing the same luminosity. And there we get about 25 million years. Okay? So, and again, this is a little more compelling because we have, but again, we have tons of, when we use different methods of aging rocks and other things in the solar system and geological processes, we create a timeline that's billions of years long, not 25 million. But at least this takes us out of the range of people. But in the early 20th century, a form of, the 20th century was really about the atom, the century of the atom. And understanding what the atom was and the energies associated with it and the structure of the atom was not something that was known to 19th century physicists or scientists, and in fact developed in the 20th century. And once Albert Einstein laid down some of the foundational work for that, they were able to say, well, what if this process, a nuclear process, is responsible for the sun? So when you looked at the nuclear potential energies, and you can see Einstein's famous equation here equals mc squared, when you look here, the nuclear potential energy in the core divided by, this is the new gas tank, right? Divided by the luminosity, which is, again, that didn't change. This gives you now 10 billion years. And 10 billion years is consistent with the sun that could exist through all of the records we have, right? And exist far into the future. And this is the consistent lifetime of the sun that fits with all of our other natural science theories like chemistry, physics, geology, biology, all that stuff. Okay, so we're going to have to look and understand a little bit about what nuclear reactions are, which is always fun times, and we will discuss that after we talk a little bit about how the sun works. I believe that's a later chapter thing, not coming up now. But are there any questions on this part that we talked about so far? Nope. Okay. So we now want to understand why the sun, even though it's so much more massive than something like, say, Jupiter, it's still much bigger than Jupiter. You can fit 1,000 Jupiters in the sun, but you might expect it being so much more massive to be much bigger. But again, as we saw with the solar system, we have this pressure. right? You can look here and see that these people are all rigid. So when you stack the people together, I've always thought this was a disturbing picture. Maybe it's just because I'm not that flexible. I think this isn't a real limb. I don't know, that shoulder looks uncomfortable. I think that's the most bothersome part of the picture right there. So you can see that these people are stacked onto each other, but they're rigid, they don't compress, right? So if you stack a person, they get bigger and bigger and bigger. But with gases, it's like the pillows we talked about with Saturn, why Jupiter has much more mass than Saturn, yet is about the same size, because even though there's more pillows, as you stack pillows, they start to shrink, okay? So there's a maximum height that you can get, right, where you're stacking pillows, and then you start to compress. And adding more doesn't necessarily make you a bigger object. Let's leave those people behind. So now what we want to do is we want to look at the mechanisms of the sun, okay? Because the sun still is pretty massive, and its gravity is pulling down to the center, all right? But there's pressure from the nuclear explosions, which is pushing the sun out. And what we're going to see is that gravity pulling in balances this pressure out, creating this gravitational equilibrium. All right, and we're going to want to understand gravitational equilibrium of a star in order to understand the structure of a star. All right, to see how they work. And this will keep a star. This gravitational equilibrium will keep a star relatively the same size, or keep it stable rather. All right, so there's the gravitational equilibrium, and then another concept is the energy balance, which is that thermal energy that's created inside is created about the same rate at which it's lost at the surface. All right, so that means that the sun stays around the same temperature because all of that heat comes from internal new nuclear reactions, right? If the sun, here's how to understand this. Say you could make a sphere around the sun. Maybe I'll even draw it here. Say you could make a shield around the sun, right? So we'll make this shield. Now, if the sun's emitted energy couldn't go anywhere, this would just get hotter and hotter and hotter and hotter and hotter, right? But it has the universe to escape out into. So the sun loses energy, and you would expect, much like a cup of coffee, that given enough time, the sun should decrease in temperature, like planets and other things, right? But planets don't have nuclear fusion going on inside them. The sun does. And so what that means is that even though the star is getting cooler by emitting energy here, that energy is replaced inside the core by the creation of new energy. All right? So that also keeps the sun relatively the same size. All right? That's basically the energy in goes or energy in equals energy out. So we sort of talked about that. Now we want to look at, much like we talked about planet structures, we want to talk about the sun structures. All right, and in some ways we know more about the sun with higher confidence than we do about planets, and that's mainly because of the nuclear reactions that occur in the center of the sun. So they're byproducts of nuclear reactions that don't interact with much matter. They're called neutrinos, and they actually give us very detailed information about what's going on in the core of the sun. And you might be wondering, well, how do we know about these? We couldn't create a sun on the Earth. That's not entirely true. We can create small fusion reactions that are unstable, that take an enormous amount of energy to keep going. So those aren't practical, but we can set them up for a little bit. And then, of course, the easiest way to create a fusion reaction is to ignite a thermonuclear bomb. That has a fusion aspect to it, and we can look at the yield of that explosion and see the same byproducts on Earth, sadly in that case, as we can on in the stars. Now, thankfully, thermonuclear weapons have yet to be deployed against people, so it's not quite as sad as what's often confused for as an atomic weapon. So the two atomic bombs the United States released in Hiroshima and Nagasaki at the end of the Second World War, those were what we call fission bombs. They were nuclear bombs, but they used the less powerful and energetic process of fission, which is when big particles break into smaller particles. Fusion bombs have a much higher energy yield, and they were constructed and tested, but thankfully never deployed. If you ever watch the beginning of Terminator 2 and you watch Los Angeles get wiped out, that would be Hollywood's interpretation of a thermonuclear explosion. And those are the types of things that, if you let off one of those in in the middle of a major city, the whole city's gone. Those are city killers. So the same process is responsible for the sun working. Thankfully, the sun is farther away. But let's look at the structure of the sun. So like planets, we have cores. This is where all that nuclear fusion happens. All right, you have this very active and hot radiation zone that gets blasted away, but then it's covered by this, it sort of heats up this convection zone. All right, so you have a convection zone in the sun in which hot plasma rises, and then cooler plasma goes down and gets heated up by this radiative layer and goes up and down while generating solar wind out. But we're not quite done yet because there are more layers. We have the chromosphere after the convection zone, the photosphere, and the corona. All right. So we want to be, we have these atmospheres, and solar atmospheres are very different than planetary atmospheres. For example, on the Earth, if you draw an Earth, hold on. If you draw the Earth and say, you're on the surface here and you go on top of a mountain, right? Usually it gets colder the higher you go up. And if you're on an airplane, which nobody would be anymore, right? As you can see, there's a reason I never became an artist. It's got propellers. Anyway, if you have an airplane and you can look at the outside temperature, it's very cold. And as you might imagine, the temperature versus altitude for Earth it drops like so, right? It decreases as you get higher up. So as your altitude increases, your temperature drops. Now in the sun, the same thing happens from the core out to the chromosphere here. The temperature decreases, but here it shoots up in the atmosphere, and then it decreases again as you go away. So there's this spike, this little blip in temperature in the sun. And no one really knows, there's not a really good explanation yet for why that is. That's one of those exciting things that we send probes to the sun to try and figure out more about. So let's get some ideas about some of the specifics here on these about the sun and its structures. So big parts of the sun, the radius is about 109 times the size of Earth. Now, to give you an idea of what that means, let's change colors here. So the volume of a sphere is equal to 4/3 pi r cubed. All right, where r is the radius. So you'll notice if our sun is approximately 10 to the 2, that's underestimating it, right? 10 to the 2 r of the Earth, then we can see here that the volume of one sun will be proportional to, well, not proportional to, that's incorrect, will be approximately 10 to the 6th the Earth. And you can see that when you take when you take this and multiply it by itself 3 times, you get the radius of the Earth cubed, which is fine, because that'll give you one volume of the Earth. But then you have to multiply the scaling factor 2 times. 10 to the 2 times 10 to the 2 times 10 to the 2 is 10 to the 2 plus 2 plus 2 is 10 to the 6th. So that's how we can understand that you can get a million Earths, volume-wise, into the sun, despite the fact that the mass is only 300,000 times that of Earth. All right? Now, the interesting thing about this, and I think the most impressive stat about the sun, is its luminosity. All right. So the luminosity is 3.8 times 10 to the 26 watts. So a watt is a joule per second, and that's the energy output of the sun. But that number can seem kind of abstract. So there's a fun calculation I like to do in the back of the envelope. And so according to this back of the envelope calculation, the sun outputs enough energy to power all of human civilization for 1,000,000 years every second. So when we talk about the sun being a renewable or nearly limitless source of information, in the way we use power, yeah, it is. Now, if we want to do something crazy like interstellar travel, well, that might require more power. But for the needs we have and the way we operate on Earth, the sun is virtually a limitless source of energy. So if you know, so I'll let that marinate for a little bit. The sun is pretty spectacular. I think it's my favorite object in the solar system. Even when I did solar system presentations, I always took the sun. That was my one to present on. Okay. So questions, thoughts? All right. So if we go back here, we can see the solar wind, which we know to be a flow of charged particles from the surface of the sun. It's our outer layer. All right. That's the stuff that creates the aurora borealis on Earth and interacts with the magnetic fields of planets that we talked about. So we've got that. Now, the corona, the outermost layer of the solar atmosphere, is at 1,000,000 Kelvin. Now, that's about 1,000,000 centigrade. If you want to convert it to Fahrenheit, you can be my guest. But it's that's not so important. It's hot, right? So this outer layer is 1,000,000. Now, you might expect that we're going to get higher temperatures as we go down, but as I told you, that's not quite how it ends up working out. And we can see here that in the chromosphere, oh, I mixed up chromosphere and photosphere. Darn it, I hate when I do that. But the chromosphere is the middle layer of the solar atmosphere. And you'll notice that we went from 1,000,000. So keep in mind here, to give this some context. So that's the same thing. It really is. I mean, I know it seems different. I just think this is a little more compact and easier to digest. The book is it's the same information. So it's yeah, for what the quizzes are based on. But you want to keep in mind that 1,000,000, which we typically write this way, right? That's equal to 10 to the 6th. So the temperature of the corona that we saw in the previous slide was 10 to the 6th Kelvin, and you'll notice that now we're going down, which is strange. That's not what happens in planets, right? And you'll notice when we get to the photosphere, which is the surface of the sun, I messed that up a little bit earlier, my apologies. It's about 6,000 Kelvin. Now 6,000 Kelvin's pretty hot, right? So that's about, let me see. Yeah, so that's about 6,300 degrees centigrade on the surface of the sun. But that's a lot lower than the chromosphere and the corona, a lot lower. So one's got to wonder, well, wait a minute, I thought you said it was all sorts of hot in here. Well, let's see what happens. We're going to see that this is sort of a minimum, all right? As we get into our next zones, we'll see that the convection energy zone transports energy upward, and what we're going to see, I don't know if they say it, but our temperatures will start to increase as we go down into the millions of degrees, all right, into the hundreds of thousands, and then the millions of degrees, and then to the tens of millions of degrees Kelvin as we get down to the core. All right, so then the core is approximately 15 million degrees Kelvin. So that 15 million degrees Kelvin decreases to 6,000 Kelvin as you get out to the photosphere, and then as you climb to the chromosphere and corona, it increases again. All right, so that's kind of the basic structure of the sun. The sun in its way is very simple because there's not plate tectonics or rock or stuff like that. It's just sort of these ranges from the core to the radiation zone, and this is all. These two are really just the this is where the fusion is happening. This is where the fusion is sort of blowing away radiation very quickly. Then it gets caught up in the convection zone for a long time, and then it accelerates through the photosphere and the chromosphere and the corona, and then it becomes solar wind. Okay. Now we have to. Now that we've introduced nuclear fusion, we really do have to talk about, or at least get some idea of what it is. Okay. So this can get a little technical, and usually when we're in class, there's parts of it I want you to understand and parts of it we can gloss over. So let's look at and get a sense for what those are very quickly here. All right. So again, like I said when I was talking about atomic versus nuclear or thermonuclear bombs or fusion bombs, fission is this process of a large nucleus like uranium decaying into smaller smaller atoms. All right? And fusion is when you have smaller atoms combining into larger atoms and releasing energy. And so lighter elements, there's no energy of fission, but you get a lot of energy from fusion. And then at a certain point, you don't get any more energy out of fusion, and that's where fission starts to dominate. And we'll see all of that in a little bit more detail. But this would fall under something you need to know, the difference between nuclear fission and fusion. And again, nuclear fission is large nuclei that split into smaller nuclei. That is nuclear fission. Nuclear fusion is when two light nuclei combine to form a heavier nuclei. All right? So that is nuclear fusion. Now, we'll get into some of the, when you look at your nuclear power plants or like your atomic bombs, that's when you get fission. You get fusion in things like the sun and stars, and again in thermonuclear bombs. There is work on a nuclear fusion power plant. A lot of this work is being done in California, and man, that work just keeps going and going and going. I actually gave a talk at the facility where they do a lot of that work, and it's described negatively and positively by all those by many involved as sort of being stuck. When I was a young student, they said the same thing about fusion as they do today, which is that it was 50 years away. So fusion has been 50 years away for the last 80 years. So looking at that, so how does fusion happen? It's basically a function of geez, I got a lot of people trying to get hold of me. It basically it's temperature dependent. All right. And you need those very, very high temperatures for fusion to happen. And so in some ways that should be scary, because we'll see that fusion is important in a lot of processes, sort of for creating heavier atoms than hydrogen, but the temperatures required for fusing things heavier than hydrogen are ridiculously high. You start to get into the hundreds of millions of degrees. So let's take a look. So at low temperatures, right, these nuclei would just repel off each other electromagnetically, but at high speeds, this can be overcome, and you can have that nuclear reaction. Now, when we're going to get technical about it, it might be tempting to think that you just get two hydrogens, or a hydrogen will fuse with another hydrogen to create the next element, which would be helium. But this is not true. This is wrong. A hydrogen has 2 protons and 2 neutrons. So the neutron of the nucleus of a helium atom is 4 times heavier than a hydrogen atom. So in fact, it takes 4 of these hydrogens, or these protons, to create 1 stable helium. All right? So we're going to look at this whole process, but don't worry, we're going to go over it, but this is the part where it gets a little crazy. So we want to know the inputs, which are these protons, and we want to know the outputs, which we'll get to in a minute. But don't kill yourself if the whole step 1, step 2, step 3 is not making sense. The overall reaction is what we want. Step 1 and step 2, 3, we'll go through it once, but we won't lose sleep over it. So basically, you do start off with 2 protons, and they form what we call a deuterium nucleus. All right. So this deuterium is an isotope of hydrogen. All right. We talked a little bit about isotopes before. That means it has the same number of protons as hydrogen, but it's got an extra neutron, different number of neutrons. So when that happens, you have, the deuterium is not particularly stable. And when you do that, you'll notice you get here, when these 2 protons collide, you get these 2 particles here. One is a positron, which is a form of antimatter, and one is a neutrino. Now, the positron is almost certainly going to very quickly interact with an electron to create a gamma ray. All right? But what happens in step 2 is the deuterium takes on a proton, and you get a gamma ray, you get more high energy radiation, and then you get this weird helium 1, because now it'll be helium, but it'll have 1 less nucleus, so this will be an isotope of helium, which is unstable, helium-3, but then that very quickly you'll get 2 of these that'll smash together, knocking off 2 protons, forming a stable helium nucleus. Basically what you need to understand is what you get out here is 4 protons, and you get high energy gamma rays, neutrinos, which help us understand the inside of a sun, antimatter, or the positron, which is pretty cool, and then you get your helium. All right, and the energy that's released is in the form of this gamma rays. All right, that's your electromagnetic energy release. Now, antimatter is pretty cool. So what is antimatter? So antimatter, so you have an electron, right, that has a charge of E, the electron, and it has the mass equal to mass of the electron. That's a very small number. Now, positron, oh, wait a minute, I messed this up. Hold on. There, that's the electron. Now, a positron looks like an electron, all right? So its mass is equal to the mass of an electron, but its charge, I'm going to write negative E. E is the elementary charge, but its charge is going to equal to positive E, all right? So antimatter looks and has all the properties of regular matter, except it has the opposite charge, all right? And that's why it's not great when they collide. When they collide, they turn in with 100% efficiency the matter into energy, and it can be very explosive. All right? So this is the overall action. You get these 4 protons in, you get your high energy radiation here, your neutrino, your proton, or your positron, and your helium nucleus. All right? Again, you might need to know the inputs and outputs of the overall reaction, but don't kill yourself too much with the individual steps. All right. So you get 4 protons in. Again, in and out, the total mass is 0.7% lower. And believe it or not, you add up all, that gives you your tremendous, remember that the E there, you lose 0.7% of your mass, but you're converting, again, with E equals mc squared. And even though m might be low, in our MKS units, our standard international scientific units, C will be equal to 9 times 10, or C squared, 9 times 10 to the 16 meters squared over second squared. All right, so in order to get the energy, you're multiplying this gargantuanly huge number, all right, with the small number here. And it doesn't matter, you're still going to get something pretty big. And that's just at the atomic level that you get all that energy out. Okay, so let's look here. So now, how does the sun, why doesn't the sun blow itself apart, and how does it keep itself together? Well, in order to understand that, we have to understand a little bit about that balance. It seems like a delicate balance between the pressure going up and gravity pulling down. But we're going to see that the interplay of these two objects keep the sun stable. All right? So we're going to see that our sun is stable when its temperature at the core remains at a nice value like it is now. But let's see what happens if the sun goes out of whack and how it restores itself to equilibrium. So first, let's look at a slight drop in core temperature. So let's say that something happens, the sun cools down. This leads to a decrease in the fusion rate, right? If you're low, that's the fusion rate is the sun's temperature. So if the temperature is rising, then that's a large decrease in the fusion rate. So that lowers the core pressure, right? The pressure eases up, which allows gravity to contract. And as gravity contracts, that makes the star smaller, which makes it heat up. And then as it heats up, the balance is restored. Okay? So we see that a drop in pressure will lead to getting us back to the normal rate. Now, what about a slight increase? So if we have a slight increase in core temperature, right, that leads to a large increase in the fusion, right? But if there's a large increase in fusion, then the pressure is pushing out and expanding the star, which leads to the core to expand and cool down, which restores a normal temperature. So we can see that it doesn't matter which way we go, we're always going to end up with this normal temperature as long as something radical doesn't happen, like we run out of fuel or something like that. And we will run out of fuel in about 5 billion years, but the Earth will be dead as a planet long before then. So the Earth only has about a billion years, I think, where life as we understand it can survive. And then I think the very outside is 2 billion. But it's expected the Earth will become inhospitable long before the sun dies. So let's take a look at how energy escapes from the sun. Now, as I said, the radiation zone, you'll notice it doesn't take a straight line. It takes this meandering path. And it only starts moving straight once it gets out. And there are estimates anywhere from a couple hundred years to a couple 100,000 years for how long it would take light to bounce around, for energy to bounce around inside them before it eventually gets out. All right. So energy gradually leaves, and we can see in the sun, what does this look like? We can see this in the form of convection in the sun. And we can see the rising hot spots, hot gas rising, and we can see cooler gas sinking along these lines. All right? And again, hot gas rises to the top. That's where a bright spot is. And notice these cool spots is cooler gas descending back down in. And that creates a convection cycle. And we can see from these different temperature gradients that there must be a rise and lowering of temperatures. This indicates very clearly that there's a convection cycle. Again, you can actually create small convection cycles in labs. And, look at the thermal properties. So it's fairly convincing. Of course, the scale of the sun is not something we can do in a lab. All right. So moving on, how do we know what's happening inside the sun? Well, besides looking at neutrinos, we can see vibrational patterns along the sun, or solar quakes, if you will. And again, there's no lithosphere or plate tectonics. And unlike the gas giants, which are covered by clouds, the sun kind of reveals itself to be bare because any clouds it would have are just being blown out. So, so because of the sun, moving in that way, we can actually see vibrations pretty clearly and see how the waves traverse the surface of the sun. All right, and you can see that the waves, some of these are moving in positive directions, some of these are moving in negative directions, and these are the ranges of motion that it's moving. So observing solar vibrations and observing solar neutrinos are how we observationally look at things, but then we make mathematical models to compare to those observations. And when these things line up, which there used to be a nice graph of this, but I can't find it anymore, but when they line up, right, you become confident in your model. And that's where we are. Now, could it be different inside the sun? Sure. But that would require all sorts of extra explanations and add-ons that make our ideas more complicated, not less complicated. So again, we are stuck, as always, with Occam's razor, which is the simplest explanation is the accepted explanation until it's not the simplest explanation anymore. Okay, and we just talked about that. Now, neutrinos are very interesting. So neutrinos interact very weakly with matter. Most neutrinos, if they come to the Earth, will fly right through the Earth and never interact with it and know that it's there. Some of them do, but they very, very rarely interact. And so, unlike the light, the electromagnetic energy, which takes a whole lot of time to get out of the sun, let's go back to that, where you had those meandering path that would take hundreds to thousands, maybe tens of thousands or hundreds of thousands of years to escape. The neutrinos, for the most part, pass right through the sun. So the neutrinos, so the light we're seeing was created a very long time ago. The neutrinos that we can detect from the sun, a couple minutes old, just as long as it takes, a little longer than it takes for the light to reach us. All right. And that's also a really good indicator that nuclear fusion is happening in the sun, because that's one of the only ways to get neutrinos. And the observation of these types of neutrinos and the properties of the neutrinos tell us a whole lot about what's going on inside the sun. We don't have a similar particle being created in the center of the Earth that can tell us about the center of the Earth. That's why I said we know a lot more about the insides of the sun than we do the Earth, with greater accuracy. So when I was in the 80s and 90s, there was the solar neutrino problem, which was early researchers failed to find the predicted number. This was a big deal. But in the last 2 decades, more recent observations find the right number of neutrinos, but some have changed form. So the study of neutrinos has actually gotten more sophisticated over the last 20, 25 years. And once we found there were different forms of neutrinos and different types of neutrinos, then all of a sudden the math started working, and this solar neutrino problem was solved. And this is a good example also of, of there being some serious objections to nuclear fusion. We knew there was some nuclear fusion going on inside the sun, right? But not enough of the neutrinos explained that completely. But so you're left with 2 choices there, right? You can either say, oh, well, it's clearly not nuclear fusion, otherwise it would be this amount. Or you say, well, let's hold on and see if we can find a better, more complete explanation. And that's what happened, right? Understanding neutrinos better in large underground detectors like this one, you'll notice those are people. Here's the detector. Helped us learn more about neutrinos, and eventually the theory and the experiment coalesced. And we now have a much stronger understanding of what happens inside the sun. And again, based on our observations of neutrinos. So we can look at this full sky neutrino map centered on the sun, produced by how do you say that, Kamiyo Kande Neutrino Observatory in Japan. And so you can notice that there are neutrinos, they interact very weakly, but you'll notice that the center of the sun is where most of them are coming from. All right, or that's where the flux is the greatest, rather. So, we've seen all that. The Sun-Earth connection. Okay, So this is the point at which we will talk about how you know, what causes solar activity and how does solar activity vary with time. Okay, there they are, goals for learning. So now what causes solar activity? I want you to notice that these are ginormous solar flares. And again, the size and scope of these are tremendous. So the Earth would probably take up a little dot right here. And I think they have one where they show the Earth later, but I think that might have been a previous chapter. So solar activity is like weather on Earth. We can see sunspots, solar flares, and solar prominences, and all of these phenomena are related to magnetic fields on the surface of the sun. You'll notice that with our solar flare, it goes up in one spot, and they all sort of loop down to another. These are the same thing as north and south poles on magnets. All right, so sunspots are cooler regions of the sun's surface, and these are regions with particularly strong magnetic fields. Okay, but you'll see the temperature in the sunspot is about 2/3 the temperature of the hotter parts of the surface. Now, if you ever looked at the eclipse before, with eclipse goggles, you can sometimes see really big sunspots if you're just checking out the sun. We have a solar telescope at LaGuardia that can see all sorts of detail of the sun. Sadly, that telescope is at LaGuardia and no one can go there at the moment. But hopefully that will change. That being said, there are ways for you to observe these, and hopefully some point in the future when we have the solar telescope out and do some solar observing, you will be able to see some of these features of the sun. That's pretty cool. Now, the Zeeman effect is a quantum magnetic effect that has to do with those energy levels of atoms. Remember, we talked about energy levels or the atomic picture of transitions. We talked about absorption and emission, and we said that as electrons move from one, as if they absorb light, they can get promoted, and if they emit light, they get demoted in these energy levels. So this would be E2, E1, E0. Well, magnetic fields can actually turn one of these lines into two very slight but distinct lines. All right, and that can allow promotion and demotion from these two lines depending on the magnetic properties of the electrons. So this is called the Zeeman effect, and it is purely based on quantum physics. And we can split these lines into distinct energy lines that are determined from different intrinsic magnetic field properties. If you've taken chemistry, and have heard of the atomic property of spin, that's what's different in these energy levels, these degenerate energy levels. So yeah, it's the Zeeman effect. So charged particles will spiral along these magnetic field lines, and we know that the sun generates a ton of charged particles, right? Because that's what interacts with our atmosphere to create aurora borealis. Remember when we saw that with the green lights above not only our planet, but we saw auroras on Jupiter and Saturn and other planets as well. And so what we have here is that the charged particles that are closer to the sun will interact with and be steered by these magnetic field lines, all right? And they can flow along these magnetic field lines. Now, these loops, so as the charged particles get stuck in these magnetic fields, they can move along an arc and create these solar flares, all right? And you can see here the loops of charged particles will start to get hot enough to radiate, and that's what will create these flares, all right? And you'll notice that the sunspots here come in pairs. One's a south pole and one's a north pole, so that the field lines can flow in a meaningful way. All right, so now this is an interesting picture that I like. This is a magnetic activity causes solar flares. It's a burst of X-rays and charged particles into space. So you'll notice that the sun does emit X-rays and some high energy light, but you'll notice it's not nearly as bright in the X-ray vision or in the ultraviolet as it is visibly, right? Visibly, it would be very bright, very orange. And we can see that. Let's go to a nice picture of the sun, because we're looking at sunspots and those other ones. You know what? I'm going to go. I've lost my patience. All right. So the picture I'm looking for, invisible light, right? Oh man, I have to go way back. There should be invisible. The sun is quite bright, right? As we can see here. But now let's go back to that X-ray picture. And you'll notice that even though we can see, oh man, so here's how bad I feel. The very next picture, there's the sun invisible. But now let's look at an X-ray. X-ray, visible. You see the difference? It's much darker looking in X-ray. But there are X-rays emitted and ultraviolet light emitted. All right, and those, of course, get flung out into space and are usually the culprit behind your sunburn. So you can see them at the source right here. That's if you go outside, which again is no longer a recommended activity. But we also want to look at these solar prominences around here. And this is what the solar telescope is really good at picking up. And it makes the sun look like, it looks like it's hard to describe. It looks like it's droopy and liquidy when you see these through the telescope, but you can see these through the solar telescope, and it's pretty spectacular. The corona on bright X-ray pictures, we can see that as a source. You'll notice it's higher in the atmosphere with the high temperatures than the low temperatures. And again, there's no clear explanation to why particles are accelerating. Yeah, no, I know, right? Well, it's called the coronavirus for a reason, based on how it looks, and it looks like a star and then envelops from its corona and kills healthy cells. But yeah, no, poor timing, right? But it's a legit astronomy term. But we can see here in the corona of the sun, it's much hotter, and there's no really good explanation for why particles get accelerated here and then get ejected out into space. So that's still something that that space scientists are trying to work out and come up with models for. None of them really quite work. Now, coronal mass ejections send bursts of energetic charged particles out through the solar system, and when these are aimed directly at Earth, they really produce a spectacular light show. Now, up until 1930, no damage. These would affect humanity very little at all. From 1930 to 1957, a little more damage and increasing damage in those years. From 1957, the amount of damage they could cause could be catastrophic. What has changed? I'm putting this to the class. What has changed about human beings from, say, 1930 or 1920 to through that time into the present? Does anyone want to take a guess? Yes.
Well, I would say the technology we use now.
Exactly. We use a lot of technology. We use a lot of technology in space. So the only thing in danger from a mass coronal ejection is electronics, is things with electronic components that run electricity and things with microcircuits. The influx of charged particles is enough to fry all sorts of circuits. We often get glanced by these things, and we have to shut down, sort of almost exactly like an EMP. Although you can shield components, you can design components, like power plants have now been designed to shield from these things if they're not operational. So the nice thing is because the mass coronal ejection moves pretty slowly compared to the light, we can tell when they're coming with a few days' notice. But the last direct hit on Earth was in the 1850s, when we were right in the middle of one, and that created auroras as far down as as Cuba, I believe. In Havana, you could see the northern lights. And while it would look cool, it wouldn't hurt anybody directly, but the loss of the power grid, I think you can see sort of based on resources being limited. We still have a power grid. We just don't go outside, and you can see how disruptive that is. If all the electricity went off, we are not prepared to deal with that. So hopefully that reality is much more than a hypothetical for this semester's classes than it say would have been last semester's classes. And you can see that we are not prepared for that to happen, at least not in this country. So they're a danger to our electronics, but in a society where our electronics are our lives, it is something to worry about. So we can see here particles streaming from the sun. This is the stream of solar wind particles. And again, this is another illustration of how the particles interact with the magnetic field of the Earth. And they deflect most of them out. The ones that do get sucked into the poles, which is where you see your aurora borealis. And it talks here about disabling electrical power supplies and things like that. Okay, so the solar system or solar activity varies on these 11-year cycles, so it's fairly predictable. Some, like seasons on Earth or hurricane seasons, some are more intense than others. And you can see here some intense solar intensities are, seasons are more intense or a little longer than others. But it's basically around 11-ish years. And you'll notice between 1950 and the late 60s, the 55 to 65 was a particularly intense solar time. What you might notice is that we're sort of entering these decreased solar intensities. So some people who like to call the sun a culprit for climate change, well, it's not quite correct. The sun does play a role with the changing climate of the Earth, but on much longer scales, and it helps fix some otherwise misleading data. But that's something you'll need to look at on your own. We don't have time to talk a lot about that. What we can look at is that the sunspot cycles are very much indicative of the, the intensity there. Okay. Now, the sunspot cycle has something to do with winding and twisting of magnetic fields. It's an important property of magnetic fields that the actual lines, like if you look at here, this sort of idealized magnetic field, these lines actually can't cross. I like to sort of, it's been a long time since there was a Ghostbusters movie, although I guess, well, they didn't say it in the new Ghostbusters movie with the women, but in the original Ghostbusters, it was a big deal to cross the streams of the proton pack. You never wanted to do it. Harold Ramis's character said it could be the end of the universe. And so that's sort of where that idea comes from, is that magnetic field lines don't cross. And basically, but the sun, unlike planets, has different rotation speeds at different parts on it. So the equator spins faster than the North Pole, than these parts, the poles of the sun. So that starts to bend and twist the magnetic field, and then it's thought that as they start to cross, that when instead of crossing, which they can't do, they just explode outwards. So that's thought to be the mechanism of what's going on with the sun. Here you can actually see the sun's, the Earth's climate, which has changed, and here you can see climate not actually changing that much. This is a graph of something that has mild climate variation from 1880 to about 2020. Well, probably 2010. This probably doesn't go to 2020. Saying it goes to 2020 is disingenuous. But you'll notice what's interesting is you can compare relatively stable climate with a gradual increase to a sharp increase in climate, right? And so you can see that you can see the temperature change here, and this is the total solar irradiance, and it doesn't track well really with the Earth's climate. It's often doing opposite things. It's what the statisticians would say that this is not correlated at all. So it's even worse than correlation does not equal causation. There's just no correlation. It doesn't matter. All right. So we've learned about the sun, and now we're going to switch scales. So the sun acted the sun acted as a, what do I want to say here? The sun acted as sort of a bridge, all right? So the sun, so we talked about the stellar, the terrestrial, the planetary scale in the solar system, and then the sun is our closest star. But now that we've talked about our sun, we have a whole galaxy and universe of stars to talk about. And so talking about stars now will increase our cosmic scale. But before we do that, I like to show a video, because remember we saw the powers of 10 back when we were still meeting in person? So I don't know if it's going to work, but I want to try and show a video and get people's thoughts on it. So I'm going to load, I'll be on here I'll still talk, but I'm going to try and load a YouTube video. I'm going to send you the link if it doesn't work. But I think we should be able to get it to work if I share my screen. So I want to make this the whole thing. I want to go to YouTube. And let's see. I'll go to size of objects in the universe. All right. Oh, hold on. There's one I really like. Oh, that one's not great. Morn. All right, so this is my favorite one, and I'm hoping I can talk over it, but I don't know. I'm going to put it in theater mode, not full screen. So let me see. Okay. All right, so I won't be able to, once I share the screen, I won't be able to see the chats or anything, but I might be able to hear them. So I'm going to ask a few of you to just chime in if you can see the movie. Well, I guess I won't know. But I'll expect silence if you can't see it, and I'll expect you to chime in if you can. So, or just type something in the thing that I can hear, not necessarily see. So I'm going to go to share files, and then I'm going to, it says share applications or screen. So I'm going to select the entire screen, and only share screen with sites you trust. So let's allow the screen share. Okay. See, it didn't like this. I don't know why. It's going down to infinity. All right. Let me just try the Microsoft application then. Let me see if I can get up. Let me see. Hopefully this works. Okay. All right. Can everyone see the movie loaded up? Okay. I'm going to say, like I said, I was expecting silence if you couldn't see it. So I'll turn up my speakers a little. I won't know if there's an echo from you hearing it. So I'm going to stop and talk through parts of it too. So here we go. So as you can see, we're going to start with the moon. And you get, you're going to see we'll start with the moon, and we get, oh, people are still talking, so that makes me think something's wrong. Hold on. Can't see anything. Same. We can't see the video. Oh, I thought you were supposed to be silenced if you couldn't see the video. But now I'm back. All right. So if I share the screen, so what can you see? Hold on. Let me go to the video and then do this. The icon. Huh. All right. Let's see here. All righty. I'm going to see if I can figure this out one more time, and then I might just assign you guys to watch the video because, if you have an internet connection, and send the link. But let me try it one more time. Well, that's the phone. Hold on. Share an application. I don't know why it won't let me share my screen. Hold on. Share window. All right, let me try this one. No, now I think I'm just sharing. Yeah, no, that was bad. All right. Yeah, no, I think I'm gonna have to give you the link. All right, so let me. This is one of those things that will have to not be as good as it would be. So link to the following video, and you should watch that one right now if you can. So I'm going to watch it, and then we'll talk about it. So I'll turn my speaker and stuff off so that I'll turn everything off. So I'll give you the next, I think hold on. It's a 6-minute video, so I'll check back in about 7 minutes, and we'll talk about it. All right? So see you in 7 minutes. I'll give everyone about another minute.
This is a real-life lore video made possible by Squarespace. Make your...
Oh, it's my computer acting funny. You think you feel tiny? Imagine how the coronavirus feels. Its influence is far, but it's very small. So in looking at the yeah, I was assuming the multiverse might be interesting. So one thing to realize is I like showing this video now because when we saw the powers of 10, we stopped at where 1970s technology could take us. But then we quickly, you'll notice when we got to galaxies, we kept going. Because since the late 70s, we have learned a ton about the universe, and we now have a much better picture. But things you should realize that you might not have realized, our big picture, our big understanding of the universe past many, our galaxy clusters and superclusters is only about 25 years old. That's from the 80s, 90s, and the last 2 decades. So I guess 40 years old now. Don't remind me that I'm turning 40 soon. It's depressing. But you can see we've gone a far way. Now, everything up to the visible universe is pretty accurate based on observational astronomy. The multiverse is a conjecture at this point. We don't have direct observations for the multiverse. There are good arguments for a multiverse. There are good arguments for there not being a multiverse. And there's no good way to measure. There are no experiments yet to differentiate between those two models. But the multiverse is not ridiculous, but it is not accepted fact either. But it's a good working model to explain some of the stranger features of quantum physics. But what you can see is we've sort of jumped from the planets and the stars. And you can see how much bigger many of the stars were than our own sun. But I hope it makes sense when I talk about galactic scale or universal scale, because you saw all of them there, right? You started with the solar system, you went to stars, you went to galaxies, then you went to cosmic scale. And so that's what we're studying. That's what we're doing, is we've left the first scale and we're going to the stellar scale. But now that you can see what that means, it makes sense to have a sense of what those other scales are as we talk about them in detail. So it's one of my favorite videos. It's always a highlight of the class for me to watch that video in class with you all. And I'm sort of peeved that I couldn't do that this time. But I'm glad you guys watched it. So any other questions or thoughts? They are almost the same size. They're very similar in size, those two planets. One is heavier than the other. I think Uranus is more massive, but I'd have to look that up. I honestly don't remember. I can look it up on my phone right now. Let's see here. Massive planets. Massive planets in the solar system. Let's see how useful Siri is. So, hold on. So Neptune is about 17 times. Yeah, so Neptune is a little bigger than Uranus. Okay. So that's weird. Because Neptune's farther away. So Neptune is a little far, but not much. So basically, they're probably around the same size, but with compression, their masses are also about the same. So they're similar planets. We have to be, now that we've looked at the cosmic scales, we have to be very clear with our words now. We can't interchangeably use them. So a way to say that is our star is not even a speck, or our solar system is not even a speck of dust in the cosmic web, because the cosmic web is a substructure of the universe. So we have to be very clear that we have our solar system, the stellar scale, the interstellar scale with stars, the galactic and intergalactic scale, and then with galaxies, and then the cosmic scale, which has galaxy structures like galaxy clusters and superclusters. And then we have the cosmic microwave background radiation, which describes the universe. And the universe contains everything. So we want to get that hierarchy correct. Otherwise, everything will get confusing. It's really easy to sort of spin down a word rabbit hole with this stuff. So, any other thoughts on the video or questions or crazy? It sounds like a few of you had your minds blown. That's always a good thing. So I think Alderaan was a star, right? So there's several types of stars. I don't think there's a galaxy Alderaan. Let me go back and look. It should have described it. Hold on. YouTube. Let me see. Size of objects in the here we go. And I can play it and turn off the sound. And I will look for your object. Earth, Moon, Mars. Kepler was a big one. Let's see here. The Sun, Sirius A, Pollux, Arcturus. Oh, okay, Aldebaran. So it's a red-orange giant. Fun fact: it's getting to its red giant phase in the future, so it's going to get bigger. So that's just a big star. Let me go back here to the chat. Yeah. So it's a big star. And you'll notice the sizes of stars can get quite extreme. So Arcturus, I think, was a different color star, and the different color stars we're going to see are due to the different temperatures. So we're going to get to the specifics there. But let me look and see, is that the next one, or do we? I think Arcturus was before. Yeah, so there's different stages of being a red giant and a subgiant, and a lot of the sizes you have accessible to you will be based on the mass of the star. All right, so we're going to see how the mass of the star dictates the life of the star. So two red giants might have different sizes based on the original star mass. Okay. So what I want to do now is I think we'll take our long break. So I'm gonna get to the I'm gonna stop recording this session and we'll come back